Hello guys, this is the EdExcel AS level maths paper 2 from the June 2019 series, and in this video we'll be having a look at the statistics section of the paper. So let's get straight into it. Question 1. We have a sixth form college which has 84 students in year 12 and 56 students in year 13. The head teacher selects a stratified sample of 40 students, stratified by year group. For part A, we have to describe how this sample could be taken. So, for part A, we have over here 84 students who are in year 11 and 56 who are in year 13. So for part A, what we do, if we consider our 84 students in year 11, we can over here label the year 12s with numbers 1 to 84, and we can label the year 13s with numbers 1 to 56. So each student in year 12 has a special number assigned to them, 1 to 84, and each student in year 13 has a special number assigned to them, 1 to 56. And the way we select these students at random is to use random numbers. Okay, so we can use random numbers to select a random sample. So use random numbers to select a random sample. And we can do this by, for example, using a computer or a calculator or anything of that sort. And in terms of the amount of year 12s we need and the amount of year 13s we need, to work out the amount of year 12s we need, we have over here 84 students who are in year 12, 56 students who are in year 13, and therefore when we come to take a stratified sample, let's just put this back into focus. When we come to find the number of year 12s we need, we have 84 divided by 84 plus 56, and remember in this question we're taking a stratified sample of 40 students, so we multiply this result by 40. So working this out, if we grab our calculator, we have 84 over 84 plus 56, and then we multiply this result by 40. The result of this is 24. So over here we require 24 year 12s. Okay, and in terms of the number of year 13s we need, in a similar way, we have 56 divided by 84 plus 56. We multiply this by 40. So let's work this out. So we change this 84 at the top to 56. The result of this is 16. So we have over here 16 year 13s. And you'll notice over here 24 plus 16 does indeed give us the 40 students. And that's all we do. Now for part B, we're given that the head teacher is investigating the relationship between the amount of sleep, S hours, that each student had the night before they took an aptitude test and their performance in the test, P marks. For the sample of 40 students, he finds the equation of the regression line of P on S to be P equals 26.1 plus 5.60S. With reference to this equation, we have to describe the effect that an extra 0.5 hours of sleep may have on average on a student's performance in the aptitude test. So we've got this equation, P equals 26.1 plus 5.60 S, and this 5.60 would represent the gradient. So let's just write that down. The gradient is equal to 5.60. So to find out what the marks will be when we have an extra 0.5 hours of sleep, the marks would be 5.60 multiplied by this 0.5. So we have 2.8 marks. Okay? And what that means over here is we have an increase by 2.8 marks. So let's just write that down. We have an increase in 2.8 marks. Okay? And now for part C, we have to describe one limitation of this regression model. So we can say over here, this model that we've just been using suggests to us that the more sleep you have, the better you perform in the test. But in reality, there may be other factors which affect the performance in the test. For example, if you revise more, the better you may perform in the test. Okay? So that's a limitation of the model. There could be external factors affecting the result. Question 2. The Venn diagram shows three events A, B and C and their associated probabilities. We have A, B, C shown here. And the events B and C are mutually exclusive and the events A and C are independent. Show your working to find the value of X, the value of Y and the value of Z. Well, first of all, what does mutually exclusive means? That means that the events cannot happen at the same time. So let's just write that down. B and C cannot happen at the same time. Okay? And if that's the case, if B and C cannot happen at the same time, the probability of the event B and the event C, that will equal 0. So B and C, if we take a look at this Venn diagram, we have 0 plus X equals 0, and therefore X is equal to 0. Now, we can also find over here the probability of A, the probability of B, and the probability of C. So let's do that. The probability of event A, if we just take a look at the Venn diagram, we have this 0.1, this Y, this 0, and this Z. All these added together gives the probability of A. So let's just write that down. We have 0.1 plus Y plus Z plus 0 as the probability of A. And if we simplify this a bit further, we have 0.1 plus Y plus Z. So let's just write that down. 0.1 plus Y plus Z. Okay. Similarly, if we go back to the diagram, the probability of B, that's the 0.3, the Y, the 0, and the X. So, the probability of the event B will equal 0.3 plus the Y plus the 0 plus the X. And we know X to be 0, so we have 0.3 plus Y. And we add on 0 plus 0. And if we take a look at the probability of C, we have the z, the 0, the x, and the 0.39 added together. So the probability of C occurring is equal to the 0.39 plus the probability, plus the z, plus the 0, plus the x. We have 0, x is 0, so we have 0.39 plus z. Okay? Now, we also have this other statement that the events A and C are independent. And if we take a look at the formula book, let's just get the formula book up. The formula book is over here. If we scroll down, it's not under the AS section, it's rather under the full A-level section, underneath the statistics bit. We've got over here, for independent events A and B, the probability of A and B is equal to the probability of A multiplied by the probability of B. So let's just highlight this. If we just highlight this piece of information, we have over here the probability of A and the probability of A multiplied by the probability of B. So let's just write that down. We can say over here, if the events of A and C are independent, then we can say over here that the probability of A and C is equal to the probability of A multiplied by the probability of C. The probability of A and C, if we go back to the diagram, A and C, we have Z plus 0, which is simply Z. So the probability of A and C, that's Z, and the probability of A, we found that to be this over here, the 0.1 plus y plus z. So we have 0.1 plus y plus z. The probability of C, we found that to be 0.39 plus z. Okay? We also know that probability adds up to 1. So let's just write that down. The sum of probabilities is equal to 1, and if we use this, we can add up everything shown over here, and we can equate that to 1. So we have over here 0.1 plus y plus 0.3 plus z plus 0 plus x plus the 0.39 plus the 0.06. All this is equal to 1. We know x to be 0. So if we simplify all this, 0.1 plus 0.3 plus 0.39 plus 0.06, you'd find that to be 0.85. And 1 minus 0.85, that's 0.15. And in terms of what we have in letters, we have y plus z, because remember x is equal to 0. So we have y plus z equals 0.15. Okay? And we've got a whole bunch of equations over here. If I call this equation 1, this equation 2, this equation 3, this equation 4, this equation 5. First of all, over here we've got a y plus z, and here we found that y plus z is equal to 0.15. So if we substitute in equation 5 into equation 4, we have z on the left hand side, and on the other side we have 0.1 plus y plus z, which is 0.15. And then we multiply this by 0.39 plus z. Okay, so with that being said, we have z equals 0.25 multiplied by 0.39 plus z. So we have z equals 0.25 multiplied by 0.39. That value is 0.0975. And 0.25 multiplied by z, that's 0.25z. So we have over here 0.75z, so z take away 0.25z, that's 0.75z, and that's equal to 0.0975, from which we can see z is equal to 0.13. Okay, so 0.0975 divided by 0.75, that's 0.13. If I call this equation 6, if we now substitute in equation 6 into equation 5, we have y plus z, so we have y plus 0.13 equals 0.15, from which we see y is equal to 0.02. Okay, so we have our solution of x, which is equal to 0, our solution for y, which is 0.02, our solution for z, 0.13. Okay. Question 5. A fair-sided spinner has sides numbered 1, 2, 3, 4 and 5. The spinner is spun once and the score of the side it lands on is recorded. For part A, we have to write down the name of the distribution that can be used to model the score of the side it lands on. Quite simply, that would be a discrete uniform distribution. So we have a discrete uniform distribution. Okay. For part B, the spinner is spun 28 times. The random variable x represents the number of times the spinner lands on 2. We have to find the probability for the first part of part B that the spinner lands on 2 at least 7 times, and then for the next part, find the probability that x is greater or equal to 4 but less than 8. So if we have a random variable x, which we know is a discrete uniform distribution, and the spinner's spun 28 times, the probability of landing a 2, that will equal 0.2, which is the same as a fifth, because we've got a fair 5-sided spinner numbered 1 to 5. So the probability of obtaining any of these numbers is equivalent. That would be 1 over 5, which is the same as 0.2. So with that, we have x over here, which is binomially distributed with parameters 28 and 0.2. Okay, so for the first part, when we come to find the probability that we have at least 7, that would be the probability that x is greater or equal to 7. Okay, and this is the same as 1 minus the probability that x is less than or equal to 6. And the reason I put this into this form is because if we go to our calculator, then if we press menu and then go to the distribution section and then press the down arrow, we have a binomial cumulative, press number 2 for variable, x over here is 6, n, the number of trials we have, 28, the probability, that's 0.2. The reason I put the probability of x being greater or equal to 7 equals 1 minus the probability that x is less than or equal to 6, the calculator can easily calculate this for us. So if I press equals, we end up over here with 1 minus the 0.6784, etc. And if we work out this value, we end up with 0.3215, etc. And for the next part, we have to find the probability of x being greater or equal to 4 but less than 8. Okay? And the way we can do this is over here, I'll do this in a different color. If we list our numbers 1 to 28, so we have over here 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. all the way up to 28. We're finding over here, if we draw this out, if I just grab a different coloured pen, we're looking over here where x is greater or equal to 4 but less than 8. Okay? So we're looking at the x values shown over here. This is all we want. Okay? So in terms of what we have to do to work out this problem, this over here is the same as the probability that x is less than or equal to 7. So we have s less than or equal to 7 minus, we don't want these first 3. So we have to subtract off the probability that x is less than or equal to 3. And we can find out these values using our calculator. So let's just grab our calculator. Here we have the probability x being 7. That value is 0.8182, etc. And then if we subtract off the probability that x is less than or equal to 3, we subtract off 0.1601, etc. The result of this is 0.6580, etc. Okay, so that's our final answer. Question 4. Joshua is investigating the daily total rainfall in Herne for May to October 2015. And using the information from the large dataset, Joshua wishes to calculate the mean and the daily total rainfall in Herne for May to October 2015. For part A, using your knowledge of the large dataset, we have to explain why Joshua needs to clean the data before calculating the mean. Well, if we actually take a look at the dataset, we're looking at Herne May to October 2015 shown here, and you'll notice, for example, here and in other parts in this category of daily total rainfall, we have these TRs, which stands for trace. So if you go back to the information given, it says somewhere over here that trace is over here, which is an amount less than 0.05 millimeters. Okay, and any data which is not available will be shown by NA. Okay, and therefore we've got something which isn't numbers in our data set over here. So we need to convert these traces into actual numbers. And I've also done that as well. If I show you, now this is available in the link in the description should you want to have a look at it. And I've also made a video on the large data set, check that out. If we take a look at 2015, and if I zoom in, notice over here, wherever I had a trace before, I replaced that with 0.025. That's the sort of middle value between 0 and 0.05. Okay? So essentially what we're looking for in this question is something along the lines of the trace data needs to be converted into numbers before the calculation can be carried out. It's as straightforward as that. For part B, using the information from the large dataset, he produces the grouped frequency table below. So we have a column labelled the daily total rainfall, we have the frequency, we also have the midpoint, and we may use that the sum of f of x is equal to 539.75, and we may also use the sum of f of x squared is equal to 7704.1875. So in this question, we have to use linear interpolation to calculate an estimate for the upper quartile of the daily total rainfall. Upper quartile, that refers to Q3. So where I write Q3, that refers to the upper quartile. Now, before we do that, what we have to do over here in this question is create another column. We'll call this column cumulative frequency. And once we know our cumulative frequencies, we can easily use linear interpolation to calculate this upper quartile. We begin with 121. 121 plus 10, that's 131. 131 plus 24, that's 155. 155 plus 12, that's equal to 167. 167 plus 17, that's 184. Now, this tells us we have 184 pieces of data in total. Now, to do this question, to use linear interpolation, we first of all need to find out which category the upper quartile lies in, and we can do that by finding the position of the median. So let's just write this down. For part B, we can find the position of the median. We have the upper quartile, so we have 3 quarters, and then we multiply this by 184. We are looking there at the 138th value, which corresponds to the median lying in the category. If we go back over here, 138 lies in between here and here. So we look across over here, the median lies in this category over here. So let's just write that down. The median lies in the category of 1.0, which is less than or equal to r, which is less than 5.0. Okay? Now, there's different ways we can approach such a question. The way I'm going to do this question is by looking at the gradient of a line. So, if I grab a bit more paper, we have over here, if I draw this out, we have the median, we have the upper quartile, which lies somewhere in this category over here. Okay? Now, if I just draw a line segment like this, okay, we've got limits of 1.0 and 5.0, okay, and we can think of those to be y coordinates, and in terms of what we have for x coordinates, we see over here we have 131 pieces of data which are less than 1. We have 155 pieces of data which are less than 5. Okay, so in terms of our sort of coordinates, we have we can think of this to be our x coordinate over here would be 131 1.0, and here we have 155 and 5.0. okay, and somewhere over here we have our upper quartile with coordinates Q3, and we're finding this Q3, and we know that the position of this Q3 is, as we worked out before, that's 138. Okay, and the crucial thing to know in this question, the gradient of this line remains constant. Okay, so the gradient of this smaller section is equal to the gradient of the larger section. Okay, so with that being said, we can actually find out these gradients and equate them to each other. So if we have a look at this smaller section, and it would help actually if I do this in a different color. If we have a look at this small section over here, then the gradient of that part, we have Q3 take away 1. So we have Q3 take away 1 over the change in x is 138 take away 131. Okay, and we know over here this will equal the gradient of the larger section being this one over here. Okay, and the gradient of that would be 5.0 take away 1.0. So we have 5.0 take away 1.0 over 155 take away 131. So we have 155 take away 131. And essentially, we're solving for Q3. So for Q3 will simply equal 5.0 take away 1.0 over 155 take away 131 multiplied by 138 minus 131 plus this value of 1. So the value of Q3, which is our upper quartile, if we grab our calculator, we have over here 5.0 take away 1.0 over 155 take away 131, and then close this bracket, and then we multiply this by 138 minus 131, close bracket, then we add a value of 1, we get 13 over 6, which is 2.17 to three significant figures. So we have 2.17 millimeters of rainfall. Okay. For part C, we have to calculate an estimate for the standard deviation of the daily total rainfall in Herne for May to October 2015. So we need to find a standard deviation estimate given this table. Now we have over here a grouped frequency table, and luckily for us, we've been given the midpoints of these categories over here. Now, the first thing we need to do is make sure that the frequency is turned on. So if we press Shift and then Menu, and then press the down arrow, and then under number 3 for statistics, press number 1 to turn on the frequency. Now, we need to input all this into a table. So if we press Menu, and then go to the statistics section, and then press number 1, we input these midpoint values. So we have 0.25, 0.75, 3.0, 7.5 and 20.0. For our frequencies, we have 121, 10, 24, 12 and 17. And if we press AC, that will store all the information in the calculator. And then pressing Options, if we press number 2 to give us a summary of those statistics, the standard deviation, which is shown here, that's 5.767, etc. Okay, so maybe if I can get a pop-up display. The standard deviation is shown over here, that's 5.76, etc. Okay. So therefore, for part C, the standard deviation is equal to 5.767, etc. And we found this using the calculator. Okay. For D part 1, we have to state the assumption involved with using class midpoints to calculate an estimate of a mean from a group frequency table. So essentially over here, what we've been using over here to estimate the mean, or if we estimate the mean, we would use these midpoints. And over here, if we use midpoints to estimate the mean from a group frequency table, we assume over here that these values are evenly distributed across each category. So in terms of what that means for an answer we should put down, using class midpoints to estimate the mean assumes that the values are uniformly distributed in each class. For the next part, we have to use our knowledge of the large dataset to explain why this assumption does not hold in this case. Now, essentially, if we go to the large dataset, let's get my edited version up. And remember, you can find a link to this in the description below, and you can also watch the video where I explain the large dataset. Remember, we're looking at the daily total rainfall. If I sort this data by clicking Sort and Filter and then smallest to largest, you'll notice essentially over here, I think some of the values have been shifted, but essentially what's happening is from 0 to 0.5, which is basically up to here somewhere, most of that are essentially, as we can see from here, they're all zeros. So because of that, that assumption does not hold, because in this first category, as we just saw, the majority of those pieces of data are zeros. Okay, so in terms of what that means in words, this assumption does not hold since the majority of the data in the first class, that being this one, are 0. Okay. For the next part, we have to state, giving a reason, whether we would expect the actual mean daily total rainfall in Herne for May to October 2015 to be larger than, smaller than, or the same as an estimate based on the group frequency table. Well, if we actually take a look at this group frequency table, we have 121 values which lie over here. Okay, and in the large data set, we found that we have a lot of values which are 0 or very close to 0. Okay? And because of that, that is, because we have a lot of values close to 0 or 0, the mean will be smaller. So in terms of what that means, in terms of words, the actual mean is likely to be smaller than the estimate, and that's because this first class, in other words this category, has more values at 0 or close to 0, and we saw that in the large data set. Question 5. Past records show that 15% of customers at a shop buy chocolate. The shopkeeper believes that moving the chocolate closer to the till will increase the proportion of customers buying chocolate. After moving the chocolate closer to the till, a random sample of 30 customers is taken and 8 of them are found to have bought chocolate. Now, Julie carries out a hypothesis test at the 5% level of significance to test the shopkeeper's belief. Julie's hypothesis test is shown below. So the first thing that she did, she stated her null hypothesis, p equals 0.15. So that's correct. The next step, she said that p is greater or equal to 0.15. That's incorrect. She let x equal the number of customers who buy chocolate, and x is binomially distributed with parameters 30 and 0.15. She then found the probability that x is equal to 8, and then she found that value to be 0.0420. So her finding out this probability is incorrect. And then because of that, because this is less than the 5%, she rejects her notch. And then she concludes that there is sufficient evidence to suggest that the proportion of customers buying chocolate has increased. Now, for part A, we have to identify the first two errors that Julie made in her hypothesis test. And we have the following problems. We see over here that the first statement incorrect. So for the first statement, Julie put that h1, p is greater or equal to 0.15. That's incorrect. It should be h1, p is greater than 0.15. The second thing that's wrong is if we assume that the null hypothesis is true, then the test statistic, because we're testing that the probability is greater than 0.15, the test statistic should be the probability that x is greater or equal to 8. Because remember over here, we're looking, of the 30 customers, 8 of them are found to have bought chocolate. So therefore, the test statistic should be the probability of x being greater or equal to 0, not the probability that x equals 8. For part B, we have to explain whether or not these errors will affect the conclusion of her hypothesis test. Give a reason for your answer. Well, if we actually calculate this, so let's just do that. For part B, if we actually calculate that, the probability that x is greater or equal to 8, that's equal to 1 minus the probability that x is less than or equal to 7. If we work this out, we have 1 minus, and then if we grab our calculator, so if we go to the distribution section, we have a binomial cumulative distribution. We have x which is equal to 7, n which is equal to 30. The probability of that occurring is 0.15. So we have 1 minus this 0.9302, etc. We find this value to be 0.0698, etc. Okay, and because this value of 0.0698, etc. is greater than the 0.05, we're in the region where we accept h0, and therefore, let's just write that down, we accept H0. And therefore, the errors that she made affect the calculation. So let's just write that down. The errors that Julie made affect the calculation. Okay? And now, with that being said, we have now a pretty tricky question, in my opinion, where we have over here, in this question, we have to find over here, using the 5% level of significance, the critical region for a one-tail test of the shopkeeper's belief. The probability in the tail should be less than 0.05. Now, to do this question, we require the formula book, okay? So just make sure you've got the formula book with you. For part C, we know already that x is binomially distributed with parameters 30, 0.15, and we're looking at over here the 5% level of significance. We can find out the mean by multiplying 30 by 0.15, the result of which is 4.5. Now, if we were to draw this out, when we talk about finding a critical region, if I draw out the distribution, we've got our mean of 4.5, and we've got some sort of a region over here where we accept H0. Everywhere else we reject H0. Now, we've got over here some lower critical region, we'll call it CL, and here we've got some upper critical region, we'll call that CU. And we need to find out this value of CL and CU. And the region over here where we reject H0 is when the probability that x is less than or equal to CL is less than 0.05, and over here we reject H0 when the probability that x is greater or equal to CU is less than 0.05. Okay? So, in terms of what that actually means, we'll write down the first statement. That is, if we look at the lower end of the distribution, say over here, then the condition where we reject H0, let's just write this down. We reject H0 if the probability that x is less than or equal to CL is less than 0.05. And we can actually find out what this value CL is using the statistics tables. So if we go to the formula book, and if we scroll right down to the binomial cumulative distribution tables, n over here for us is 30, and we're finding the x values. So if I grab my highlighter, we're looking over here at n equaling 30, and the probability is equal to 0.15, so we're looking down in this column. Now, you'll notice over here, if I grab a different colour, for this condition, looking at this column here, where we have a value that's less than 0.05, that's over here at 0.0480, to an x value of 1. So we can say over here that from the tables, the probability that x is less than or equal to 1 is equal to the 0.0480. Okay, and we see that this 0.0480 is less than the 0.05, and therefore the lower critical value, or the lower critical region, is equal to, rather, the critical region is when x is less than or equal to 1. Okay, that's our first critical region. And similarly, if we consider the upper tail, sorry, this should be in a different color. If we consider an upper tail, then we have over here where this region where we reject H0. Okay, and in terms of what this means, we over here reject H0 if the probability of x being greater or equal to Cu, because remember we want over here values greater than Cu, we reject H0 if this condition is less than 0.05. Now the problem is over here, as with binomial distributions we saw in previous questions, whenever we have x being greater or equal to a certain value, we sort of change that round to say that over here the probability that x is greater or equal to Cu is the same as 1 minus the probability that x is less than or equal to Cu minus 1. Okay, and the reason we subtract 1, say this value is 20 for example, then the probability that x is greater or equal to 20 would be 1 minus the probability that x is less than or equal to 19, and remember 19 is 1 less than 20. So essentially we have to flip this condition, and essentially over here you'll see that 1 minus the probability that x is less than or equal to Cu minus 1 is less than 0.05. If we rearrange this, we can therefore reject H0 if the probability that x is less than or equal to Cu minus 1 is less than is greater than 0.95. Okay, so let's just actually typex this for clarity. We're looking at when the probability that x is less than or equal to Cu minus 1 is greater than the 0.95. Okay, so let's just put the camera back into focus. So that's our next condition over here. And if we take a look at the tables, so from tables, if we go back to our tables, where we have a value that's greater than 0.95, if I grab a red pen for example, that's over here at this 0.9722, and that corresponds to x equaling 8. Okay, so from the tables we see that the probability that x is less than or equal to 8 is equals, let's make use of this typex again, this over here equals 0.9722. And what we see over here, that this 0.9722 is greater than the 0.95. Okay? And from this 0.9722 corresponds to, well, this 8 over here corresponds to CU minus 1. So let's just make that clear. This 8 over here corresponds to CU minus 1. So CU minus 1 is equal to 8, and therefore CU is equal to 9. Okay? So with that being said, we can therefore conclude that our upper critical region is when x is greater or equal to 9. Okay? So in terms of what that means in terms of a diagram, if I draw out a distribution, we've got a region here and here where we reject H0, and we found over here that this over here is 0.0480, and this over here is 1 minus the 0.9722, because remember, this over here, this x being less than or equal to 8 will be everything over here, not including this bit over here. So therefore this bit will be 1 minus this, which is 0.0278. Okay? And that nicely brings us on to part D, where we have to find the actual level of significance of this test. The actual level of significance would correspond to this percentage over here, which is, well, the actual levels of significance, we have the 0.0480 and the 0.0278. Okay? So that concludes the end of the paper. Don't forget to like, share and subscribe. I'll be going through the mechanics paper in the next video, so please click the link in the description to watch that video. Hopefully that should appear on the screen if I've edited the annotations correctly. But anyway, thanks for watching. Thanks for watching rather. Hope you found this useful.